this first. Okay, so the first problem says you want to find the maximum volume of the cone that can be inscribed inside a sphere of radius. So you've got the sphere, radius r, and you put a cone inside. Right now, of course, this cone can be really long and skinny, tall and skinny, or it can be way up here in the northern hemisphere and short and fat. And somewhere in here, hopefully, there's a maximum volume. Right. So the first thing I would do, a picture really helps out here. And if you take a cross section of this, if you cut this cone and strap down the middle, it looks like a circle with a triangle inside. Everybody agree with it? Something. And the circle that's the equation for the circle where the solid center is 0, 0. Everybody okay with that? Now, let's label this point. I mean, I know what this point is, right? Because it's at the top of the circle, it's x coordinate is 0, its y coordinates are. But this one can vary. As you vary this, as this point goes down here, it becomes the tall, skinny cone. It goes up here, it becomes the short, fat cone, right? Now, given my label here, my question is what is the volume of this cone? So the volume of the cone is, I gave this to you. If the radius is r and the height is h, volume is 1/3 pi r squared h. So in fact, when you use this formula, I need to know what the radius and height are. What's the radius of this cone? Do I agree it's that? What is that? In terms of crap that I got wrong on the picture. X. This is a little trickier. What's the height of the cone? Everybody agree that's the height? So what is it? How tall is that? Did that off quick, but you do that. Right, it's just the difference. This measurement minus this measurement. That's what we're doing here. What's the y coordinate at the top? The y coordinate at the top of this thing? Should be the same as radius of the circle, right? R. What's the y coordinate at the bottom? There it is. It's y. So the height is just this minus this. R minus y. You know what? You can gut check yourself on this. So ask yourself this: what happens when this y coordinate is at the North Pole? Y coordinate will be r, and your height will be 0. What happens when your y coordinate is at the South Pole? Well, now your y coordinate is negative r, and r minus r is 2 r's. What happens when y is right at the equator? Y equals 0, r minus 0, you get r. Right? So this makes sense. That's a good thing about math. Once you get comfortable with it, there's lots of checks. Right, okay, so this is actually the steepest part of the hill, I think. Because from here on out, the calculus and stuff is easy. So let's use this formula. The volume is 1/3 pi, radius squared is x squared, times the height, which is r minus y. And what problem do we have facing us? Too many variables, right? Got x, got y. What are we going to do to alleviate this problem? Right, use this equation, right? Do you want to solve for y or solve for x? I want to solve for x, right? You can do it if you solve for y, but that's going to involve r minus some crazy square root, right? This thing, in terms of x, well, x squared in terms of y, it's that. That's much easier to implement. R squared minus y squared, r minus y. But okay with it? Now, at this point, let's take a derivative. Oh, wait a minute. Even I got a little too excited. What are my acceptable values of y? How big can you be? How small can you be? Is there no limit to that? Like strengths. Maximum R. Yes. The biggest y can be is up here at the top, R. What's the smallest it can be? Well, that would give you something that's like got its bottom at the equator, but you can go lower, can't you? How low can you go for the y? Negative R, go to the South Pole. That's got me excited because this is a continuous function on a closed interval. So this is one of those deals where all we got to do is find the derivative, find the critical numbers, and then plug in some stuff. So 1/3. I'm going to use the product rule in these two values here. This is going to be minus 2y, r minus y, plus 1/3 pi r squared minus y squared times negative 1. So this is, let me massage this. I can pull 1/3 pi out. This gives me minus 2y r minus y plus minus r minus y r. So I pull the 1/3 pi completely out of this. This leaves me the first term with minus 2y r minus y. And in the second term, I wrote this as r minus y plus y. And now, the reason I'm able to do this is now I see a common factor of r minus y here. And I'm going to pull that out. This is minus 2y. This is minus r minus y. So finally, I get the derivative. It's 1/3 pi minus R minus 3y. Well, okay, so any questions? This makes a critical number, or whose candidates one of the without. It's like, they come to zero, don't they? What does this give you? Y equals R. What does the other one give? That's right. Setting the other one equal to zero, you get 3y equals negative R, or y equals minus 1/3. Two critical numbers. And one of them, are they in our range? Are they in our playground? Yes, and minus 1/3 R, yes, they're in our playground, both of them. One of them happens to be an endpoint, so that makes life a little bit easier. So all we gotta do now is check this out. So there's the endpoints, one of them. And of course, notice, look at the volume formula. You plug in y equals either plus or minus R, this term gets zero. So I know what's gonna happen, right? I'm going to get a max if I get anything other than zero from this. If this gives me anything other than zero, it's a max or a min, something, min. So it's gonna be 1/3 pi times R squared minus, when I square this, I'm gonna get 1/9 R squared. And then I'm going to get R minus minus. So this gives me, that's gonna be 8/9 and 4/3 is 32.7, 32.8. And by the way, I think I did ask that problem, what's the height, what's the width, or the radius, for the height. Remember, that was R minus Y, which is R minus 1/3 R. One-third R is not taller than. And the radius is X, which is the square root of R squared minus Y squared, which is the square root of 8/9 R squared, which is 2 radical 2 over 3R. I don't know about you all, but this makes sense to me, because if you've got the cone up here, it's just not going to be tall enough, right? In fact, notice that if you have the cone here, then right down here, you have a bigger cone, right? Because down here on the symmetric side of the sphere, it will have the same radius, but it'll be taller, right? And what the R is minus 1/3 is like, okay, you've got to go south of the equator to get your biggest cone, and that makes sense. So this all kind of influences. Everybody understand what we did? That's the height of this cone, right? So how do you measure the height of something like this? How tall is that? That's you. How far corner minus bottom y coordinate? What we'll do here. What's the top y coordinate here? Well, that's the 0 R. Top y coordinate R. What's the bottom y coordinate? It's the y coordinate here, which is y. And like I said, you can check this, right? So think about what happens if y is 0. If y is 0, then this point sits right at the equator, and the height is exactly the radius of the circle. If R is, if y is negative R, then it's not really a cone anymore, it's a stick. And it's all the way to the South Pole, and now the height's going to be 2, right? Which is R minus 1. Okay, other questions? On this one, you're driving down, okay, so I'm gonna read it and we'll try to draw a picture of it. You're driving down a long straight road and approach a billboard. The billboard is perpendicular to the road, 60 feet wide and 30 feet from the road at its closest point. We want to find how far from the closest point on the road to the billboard you are when you get the best view. Okay, so let me try to illustrate what that is. How many of you have ever done this? You drive down the road, you see a billboard, right? And you don't bother to read it when you're a mile away because you can't read it. But then when you get up close, there's a time when you want to look at it because once you go too far, you can't read it anymore. Right? So here's the situation. You're going down this road here. There you go. And there's a billboard. It's 30 feet off the road. And it is 60 feet wide. And here you are coming down the road, and you're looking at the billboard. So I hope you're passing. Now, by the best look at this problem, we mean when is this angle biggest? When does it fill? When does this fill your vision the most, if you will? We're going to call that best look. You can argue about it, but our best look would be that this angle is as big as possible. And notice what happens if you're 40 miles down the road. This is going to be a tiny angle, right? And when you get way the heck up here, it's going to be a tiny angle too, right? You can't see it when you're almost. And so somewhere in the middle, it seems common sense dictates that that angle, since it's really small, somewhere in the middle is going to be big as possible. So what we want to do here is maximize theta in terms of the variable x, where x is my distance between here and this point on the road. Some value of x. There. Everybody on board. Here's the hard part of the problem. The hard part of the problem is stuff that ostensibly is not very out. How do I get theta? Don't you wish that that billboard was right up against the highway? Right? Isn't that kind of what's killing you here? Because see how wonky this triangle looks? That's the problem, isn't it? Well, again, this is math. You can do anything as long as you don't break the rules. Let's make the triangle go against the highway. Let's call this angle alpha. And let me write a genius equation. You're going to marvel at my geniusness. Everybody would have to agree with this. Theta plus alpha, take away alpha. What is the point of this? This whole angle is theta plus alpha. So really what I'm trying to express in this equation here is if I want to figure out what theta is, figure out what all of this big one is, and take away the blue one, right? And the good thing about this big angle and this blue one is they're part of a right triangle, and that I can deal with. So for example, let's look at the triangle for a moment. So let me show you how to kind of pull out what you need here. Okay, think about trigonometry. Remember, this is right. What is the tangent? If you were in trig class, what is the tangent of that angle out? I agree. What is the tangent of the big hole? Okay, everybody with me on that? Right, the tangent of this opposite over adjacent 30 over x with the tangent of out. Tangent of the whole big angle is opposite over adjacent, so it's 90 over. Okay. So I can find alpha benefits off of this way. So let me rewrite this. Alpha is inverse tangent 30 over x, and theta plus alpha is tangent inverse 90 over x. So here is the formula that I have. This minus this, so I get tangent inverse 90 over x minus tangent inverse 30 over x. Okay, everybody okay so far? What are my acceptable values of x? Any positive number. You can think of this in a couple ways. You can look at this. Is it clear from this equation, this function here that it's got a problem at zero? Zero's been a problem, right? And you can also think about this sort of physically, because think about driving down the road. You can go as far back, and you may not be able to read the billboard, but it's still got some really tiny angle, right? For sure. And then when you get up here, the problem no longer makes sense anymore, because now you pass the billboard. So this one's a little problematic because this means we can't play with the physics like we did last time, but we will persevere. Let's take the derivative. What's the derivative of the inverse tangent of blob? Right. One over blob squared. It's 1. But I'm not done. I've got to multiply by the derivative of blob. Now, the blob here is 90x to the minus 1 power. So its derivative is minus 90x to the minus 2. It's all right that way. Let's see. Now I got to take the derivative of the other thing. And the derivative of the other thing should be the same as this derivative with 2 differences. Number 1, instead of 90, I've got 30. And number 2, there's a minus sign. So it should be minus 1 over blob squared plus 1. Minus 30. I know this is horrible, but it's really not so bad. Multiply this x squared through, and this is minus 90 over 8100 plus x squared. This is plus 30 over 900 plus x. Now, the best thing to do is to find a common denominator here. Don't worry about multiplying this together. Multiply it out. So it's going to be, that's going to be minus 81,000 minus 90 x squared. Multiply that by that. Get the appropriate numerator. And this is going to be 243. So theta prime is equal to 8100 plus x squared by 900 plus x squared. And what do I have on top? So if I'm looking for critical numbers here, I don't find any on the bottom, right? It's possible to make that bottom 0, square root 0. So the only thing that critical numbers, I just need to set solve that. If x squared is 2700. Yes. And so x is plus or minus. But of course, we only need the plus 1. 35. So the square root of 27. So I only get one critical. Whatever the square root of 27. Now, I believe the problem said, what does the problem say? It says, how far are you from the closest point on the road to the billboard when you get your best look? It doesn't ask what the angle is. It just asks, where are you on the road? How far away are you when that angle is as big as it's humanly possible? I get one critical number. Don't forget to check it. What if this makes a minimum, right? We want a maximum. You can verify that this makes an absolute maximum. So check this out. 0 is not in my range. I only got one critical number, and it's this 30 right to 3. This is theta prime theta. Okay, so let's look back at our derivative. What happens when you're stinking close to zero? Then positive, 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 so what happens when you're a huge negative on the other side of zero? Well, positive, positive, and if x is big enough, then certainly this is going to be negative than nine. Right? So actually it's critical number, it's negative. So what happens to theta? It increases and it decreases. Just like we thought it would, right? As we drive, well, as we go this way. So this gives a local max, and actually it's an absolute. Because it's the only critical number on the range, and so it increases until it's at maximum and then it decreases. Of course, this is running in the direction back from zero. You've got almost zero for an angle. Your angle increases until you get right at 30 radical 3 feet point, and then as you go off to Vegas, the angle decreases and decreases. Okay, any questions? Yeah, there's always going to be two kinds of problems, right? One is when it's a continuous function on the closed interval, in which case all you gotta do is plug in critical numbers, the original function, the inputs, the original function, and compare who's big, who's small. That gives you your maxes and min. And then you've got this other kind where you get a critical number like this one, and you've got to make some kind of qualitative judgment. Okay, I know this is max because, I know this is min because. Okay, then I asked a Newton's method question. So we had the function f of x, x cubed minus 3x. And I drew this for you to hopefully help you out with that. This is what it looks like, sort of. Okay, question A. The first question was, what value should not be chosen for a first approximation? Why not? Initial x not so 5. Somebody tell me what the one is. Next approximation is the previous approximation minus f of the previous over f prime. This formula often reminds me what I don't want to put in. What would be a problem here? If you have a zero derivative, right? So let's see what the derivative of this is. F prime of x in this case, what? what do we not want for a perfect approximation? Or negative. Because at these places, the derivative is zero and the formula doesn't work. Basically, what happens when you get a zero derivative is the tangent line is parallel to the x-axis and you don't get an x-intercept, right? One of two things happen. You either don't get an x-intercept at all, or you're actually on the x-axis. Everybody okay with that? So we don't want plus or minus one because it makes the formula blow up. If the initial approximation x0 is chosen between 1 and 1.1, describe the behavior of later approximations. Which root will approach and above or below? Okay, so let me draw a picture in here. We know from part A, say this is 1 and 1.1, not the scale, it's very close to it. If I choose the initial approximation in this one, I choose somewhere up here, what root is it going to approach? If I choose it in between here and here, everybody agree with this being the next approximation? So this is x0, this will be x1. And then the next approximation next. So what's going to happen? Which roots are going to approach? This, which is actually radical 3. It'll approach radical 3 and it will do it from above. Right? Notice all my approximations hit on the x-axis to the right of the root because of the concavity. Everybody okay with it? Now, the next question, if the non-zero approximations of Newton's method were to approach zero, suppose, because notice zero is the root of this, isn't it? Right? So it says the non-zero approximations of Newton's method were to approach zero, would they approach from above or below and why? By the way, this one, what's the second? Great. So what happens if the approximations of Newton's method approach zero? They come in from above or below? That's a trick question. That's right. They come in from above. Because notice the function is concave up here. And it's concave down here. So if this is one of the approximations, x1 say, because it's concave down, tangent line is on top of it, parallel. So it goes into here. That's good. But now, the function is concave up, even though they draw it there. So the tangent line is on top of the function, so it goes on this side. And then on that side, But what happens is, it's concave down here, pops it over here where it's concave up. So it pops it to the wrong side of the road, just keeps going in like this. Whatever. And again, it's going to be concave. As the initial approximation, x zero gets closer to 1 from the left, what root does Newton's method begin to approximate and why? One more picture. Okay, so here we have 1. Now, as you get closer and closer to 1 from the left side, really close, but not 1 cell, what happens to those tangent lines? They actually hit over on this side. So what happens if you get closer and closer? Eventually, if you get all the way to 1, the tangent line will be parallel and never hit. But as you get closer and closer to 1, it pushes you further and further off the negative x-axis, right? And once you're over there, you come back into this root over here. So if you get very close to 1 from the negative side, the tangent line gets flatter, gets more and more to horizontal and actually intersect on the negative x-axis. And once you're over here, just like in the previous one, because of the concavity, then the root comes into this one right here. And actually, it'll approach the root from which side? From this. Below, right? Because notice all the blue ones are on the left side. They're all below. On the approximation. Okay, any questions? Okay, other questions? So what do you got on?
Just asking.
Yeah, so let's certainly look at that. Take a look and see what. All right, well, with the other side, I guess. So has anybody tried any of these problems? Yeah, sorry about that. You know, the guy came by to fix it today and it's fixed, so I just have to call it in. Actually, this might be a good exercise. Um. That's really weird. And in fact, I did it exactly the same way. I didn't even look at that. Number four is probably just dead. Funny how the brain works. Um. um, let's do number two. Why don't you guys try to work out number two? Yeah. Yeah.
Margin.
Yeah, I think that's, I think that problem number two. So what problem number two says is poster is to be, maybe I corrected, I hope I corrected it, the test. Need to fix that. A poster is to be made and printed, and the printed area is to be 64 square inches. Oh, the printed area. No, there probably isn't a mistake. So the printed area of the poster has to be 64 square inches. If there's a half-inch margin on each side of the printed material, what is the minimal total area of the poster? Okay, so this problem is a little bit more sense. Let's see how it works out. So how would we set that up? So you had a question, obviously. You thought about this. Yeah. Well, so, right, everybody's had a poster in their bedroom or something when they were a kid, right? Have you ever noticed that the posters, they'll have a picture on, and there'll be like a margin, be like some extra white stuff or whatever along the edge. Right, I guess they do this so that they don't cut off part of the printed material and make whoever they're selling the poster to mad. So the situation we have here is we have a poster is printed area is to be 64 square inches. And there has to be a half-inch margin on each side of the printed material. What is the minimum total area of the poster? So you want to, you want to sell your 64 square inches to, whoever likes posters of, whoever, Ariana Grande or whatever. But you want to make this with as small a poster as possible because you want to save money, right? So you want to put the 64 square inches on there, make the fans happy, but do this with as little amount of poster as you can. So let's see what we got here. You know what? When you don't know, draw a picture. It's supposed to have a half-inch margin on each side. And I don't say it, but I guess we're assuming it's supposed to be rectangular. So this is the printed material here. This should be 64 square inches. Now the margin is supposed to be a half inch, right? So this is 1/2, 1/2, all the way around. So that's what's in it. So we're making a poster. Here's the stuff people want to look at. This is my safety margin, has to be a half inch, right? And what we want to do is minimize total area of poster. Okay, so what do we got here? Let's say, poster to be made 64 square inches, printed area, got that half-inch margin on the side of the material. What is the minimum? So let's call this X, this Y. So. Let's gather some facts. What do we know? What's a piece of information? Okay, which area? Of the printed area, right? And so, and what's the printed area supposed to be? How big is the printed area? Okay, good. So I got that. That X Y is gonna be 64. That's my picture of my team heart valve, right? And what are we trying to minimize? I'll say, hey, the total area. What is the total area? of this thing? Well, I guess we need to know how long this is. And how long this is. How long is it? Y plus. There you go. Y plus 2 margins, so Y plus 1 each. Right? Good. Okay, so this is what we're talking about. Uh, what's my problem here? Too many cotton picking variables, right? What can I do? Very good. Okay. So my new and improved. Might be easier to multiply this out, figure it out. Yes, it's going to be 4 plus X plus 64 over X plus 1. So my A is equal to 65 plus X plus 64 over X. What should I do now? Let's figure out what our playground is. How big or how small? I think making it small is more, except you can't really make it 0, right? You got a serious problem 0, right? Because actually, if you make it X 0, the printed area is 0, and everybody will be angry about that, right? So how big can you make it? You can make it as big as you want, right? Because the other extreme is like letting Y be very, very small, right? And that's to be miles long. Nobody's gonna buy your 3-mile long toaster, but you could do it, right? Like, typically goes 0. So now I know what I'm doing. This is what I want to minimize on this interval. So let's take a derivative. Bring this 0 is 1 minus 64 squared. Because this is 64. This is 64x minus 1. Prove this is minus 64x minus 1. So a critical number that leaks out at me, a potential critical number is x equals 0, but I don't have to worry about that because that's not our domain. So no worries there. So all I've got to do, drive this train, set the secret 0. X squared. 64. Actually, X minus a. I can scratch the minus a off. Because it's not acceptable. So what's the minimal total area? Oh, I guess I should make sure that this is minimum. What was our maximum total area? I'd be so fired if I made that as big as possible. So let's see here. A prime A. One critical number at A. Let's look at this derivative. What happens if you're very, very near to, well, what happens if you're on the left hand side, right? Say one, plug in one, this is put it in positive. Oh, whoops, I plugged in the wrong thing. Try that again. No, yeah, plug it in function. Careful. What happens if out to the left base something like one, if I plug that in, I'm negative. What happens if I plug in something that's beyond eight, something like 10? 1 minus 64 over 100 is positive. So A decreases or increases. So this is a local min. So it's actually an absolute min. Now, what did the question ask? It asked, what is the minimal total area? This should be A of 8. It should be whatever you give them for the 8 this morning. So this should be 65 plus 8 plus 64 over 8. So that's 81. Yeah, that's right. Because, so here's what happened. And by the way, what's the shape of the printed area? It's a square, right? Because we got what? We got X is 8, so that means that Y is 8. So this is actually square, right? So this is 8 by 8, and then another half inch in either direction gives you a 9 by 9 square. So. What's that? You didn't know it was a square. That's the problem. Everybody okay? Okay. Oh, and look what I did in number 1. So I guess if you'd been taking the test, you would have done number 1 first, which I actually obviously did to help you there. Find the domain because notice number 1 was sort of graphing. By the way, this is good practice. Let's sketch the graph of this. So, done the practical problem. Let's see what this is. We've already done the derivative of this. We got like 1 minus 64 over x squared. And second derivative of this turns out to be 128 over x squared. Critical number. Plus or minus a, you got that over here. We also need to check zero, because the derivative could change sign. And the important number here, check, is x equals zero. Because that's the only place. So let's look at a sign chart for derivative. Actually, I've sort of done half of it over here. Be negative, positive. And when you change over sign, so this is F, so this increases, decreases, decreases. This is a local max. And what is those? What is the signs? What do you mean? Yeah, it should be vertical axis, but you get very close to x. I'm sorry, when x is very close to zero, this is becoming huge, either positive or negative, depending on the sound. This should be a vertical axis. What is the limit as x goes to infinity? Left of x. Great. How about it's negative infinity? It's also it's negative infinity there, but you can actually be more specific, right? This actually has a slant axis. Because this piece goes to zero. You remember that I was talking about that? So what this means is this function for very, very large values of x, either positive or negative. That thing was very much like x. So y equals x is a slant. And that's kind of the content of the first question. I'm sorry, the second part B on this question. Let's look at the second derivative. We have one important number before that's zero. And it looks like negative, positive. So the concave down, concave up. Is that something that we're made of proud? Yes, it goes into the place. Well, yeah, you guys got fun right? Yeah, yeah, let us know all the time for when you guys. I would be too say this is a point of inflection, but it's not as vertical as but the concave of this change, there's no point. So let's try to graph this. The line y equals x is a slant axis.
That's the previous sound I've ever heard. Let's keep getting this. No.
So, I'm not gonna do a good scale here on this. We have a local min at the point eight, whatever I get my point eight here, so it'd be 16. And a local max, what, negative 16. So maybe right here. So what does it look like on this side of zero? It's always increasing off the asymptote until it hits that local min, then it increases, and it's always smiling. It goes up to something. And this is an odd function from here. On this side, what happens is you increase coming off the same asymptote, you hit the local max. So more. Everybody okay with that? Is that clear? Which one? 3?
Yes, sir.
Okay, so it says a rancher has P feet of fence from which he needs to make a rectangular pen divided into 2 smaller rectangular pens. Explain how he does this to maximize the area. So he's got, yeah, we did this 3, so it'll be good to see it. Like this. So whoever this person is has P feet of fence. Needs a rectangular pen containing 2 smaller ones. And the question is how does he do this to maximize the area? So let's see what he's got here. He's got to make this. There's a rectangular pen. He's got to make 2 smaller ones. I didn't really say equal size, but it doesn't matter. Does it? Because whether I string this here or string it here or all the way over here, I'm still using the same amount of fence, and the total area is the same. It's really wrong. Okay, so let's call this length right here y. And let's call this whole length x. So the farmer has P feet of fence. So interpret that in terms of the picture that I draw. So my P of fence is what? Right. To make this fence, he needs 2 lengths of X and 1, 2, 3 Ys. Right. Okay. And what is it we're trying to maximize? What is the area of this the total shebang area. Next time. And we've run into our usual problem. Because I got too many variables. So you can sub out for X, you can sub out Y, it doesn't matter. I'd rather divide by two, so I will say that X is equal to 1/2 P minus 3/2 Y. Solving this X force, and now let's put the solve together. This is going to be 1/2 P minus 3/2 P of Y. Y. So, let me kind of organize my thoughts here. One half P minus 3/2 Y. It might also be right at this. Okay. Now I need a playground. What's my playground for Y? How small can Y be? Right? Think about what's going on. If Y is 0, well, the farmer's kind of a dork because he squandered all of his fence. He took half of it, ran it this way, and then ran half back. He's not going to be able to put any cows in that. Right? Other question: how big can Y be? Be a little bit careful on this. What's in it? You make Y biggest by making X. Because X, the smallest it can be a 0. Now solve that for Y. Y is 1/3 of P. Right? Think of it this way. When X is 0, what has he done? He's taken 3 lengths of this and just run them right on top of each other. So it's 1/3 of the amount of fence he's got. Right? Okay? So now you take derivative and I get 1/2 P minus 3 5. And notice I only get 1/3. I set the sequence 0. I get 3Y is equal to 1/2 P, and I get 5 equals 1/6. Now all you gotta do is check. Now, if you think about what we're doing, when Y is 0, this should give you a 0 area. And when Y is 1/3 P, that means X is 0, you should get a 0 area. Let's see what happens. Let's look at our area formula. When Y is 0, this gives me 0 because of that. And when Y is 1/3 of P, then 3/2 of that is 1/2 P. 1/2 P minus 1/2 P is 0. Finally, here's the one critical number, at 1/6 B. This gives me 1/2 B minus 3/2 of 6 is 1/4. And times 1/6. So half minus 4 is 4, so I get 1.4 squared. This is the maximum. Oh, no, it's not what he has. Explain how he does it. Okay, there's your maximum area. How does he do it? Taking y, our picture, 1/6. So, and then I guess x would have to be 1/4, I guess. So it's x is 1/4. That's okay. Yeah. Well, you should have. I mean, it doesn't matter what you call variables or anything else, as long as, yeah, another thing you could have done, the way I did this last time, is you could have said, you know, I think I did this when I did the 3-10 problem. I assumed that they were, I think I may have said they're all equal size. I think I did x, 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 y. So that's 6x is 4y's or something like that. You do this way. However, one of the problems is you don't know this is the same length as this. Like, so this is, and it's easy to do. Okay, other questions?
Says I have a function f(x) prime 0 to infinity. And I know that, and then it gives you the derivative of the function. When it says the most general form, I assume that's just anti-curve, right?
Yeah, and most general form should be like with a plus C. So, did you figure that one out?
All right. Exactly.
Well, this one does. So, the only piece of information is this.
And one is
2x squared plus 1x. No, I don't get that to you until part B. Let's find the most general form. I did probably say that it's fine, all on 0 and 10. So, x. How would you do this? So, which one of these pieces you got? Oh, you need to put it over a single denominator? Yeah. You certainly can do that algebraically, but I think it's gonna muddy the water. It's just gonna make. Right, what you want to do, break this down? Correct, right? Everybody agreed the antiderivative of 1 over x plus 1 is equal to 2. So then this should turn out to be 4. This one does. using. Algebra could now be used to help you out. Anybody write this fraction in another form? Notice there's just a single thing in the denominator. So isn't this 2x squared over x plus 1 over x? So this is 2x. It's just a fancy way of writing it. That's right. This is now it's much easier to see what to do, right? So oftentimes the algorithm simplifies things for you. This is 4 inverse tangent of x, that's predicted, plus x squared plus natural log. And actually, you don't really have to write the absolute value because x is bigger than 0. And I forgot something. So I did say the most general form. And in part B, it says, now suppose f1 is 0. One, 4 inverse tangent 1 plus 1 plus log 1 plus c. Let's see if I can figure out what that is. 0 is, this is power 4, so this is half 1 log 1 0 plus c. It's c minus pi 1. And the function is in all its glory. F of x is 4 inverse tangent of x plus x squared plus natural log to the value of x minus 5 minus. Oh, so this is just something that maybe, so let me ask you this, do you know what the tangent of power 4 is? That's this. Right? Because if you think about circle trigonometry, power 4 right there, and at that point the sine and the cosine are equal. So tangent power 4 is 1, so that means power 4 is the inverse tangent. And there's like, you know, 3 or 4 values that are familiar. You should probably know that just for the good culture and all that. But if you left this in the form 4 inverse tangent 1, you would not be incorrect. It's a number. Number 5. So it says the high tower of Isengard has a conical turret, the height of which is exactly twice the radius. If the radius of the tower is 24 feet and the roof is covered with a 1-inch thick layer of ice, approximate how much the ice weighs. We will assume that ice weighs about 60 pounds per cubic foot. Is your estimate an overestimate or underestimate? Briefly explain. Okay, so it's also, I'm going to put it here. I've got a cone, so I'll remind you. The radius R, height H, volume is 1/3 pi R squared H. Okay, so now. What do we have here? The height is exactly twice the radius. Okay, the radius is another point. So you've got this. So let me caution you a little bit. This is it's very tempting to write 24 feet as radius. And that's true of the original tower, right? But you're always safer to have variables in here. And you probably should in this case, because in this problem, things are changing. Because you've got the tower, the original roof, and then you clump some ice on it. So that changes the size of the tower, doesn't it? So always be safe and do that. Let's see. So we'll say the radius is R, because that's safe. We're going to use 24 later, perhaps. And what do we know about the height? The height is it's twice R. So let me label this appropriately. This is actually 2R. So let's use this with our formula. Volume of my tower is 1/3 pi R squared times the height, which is 2R. So actually in this case, we get 2/3 pi R. Everybody okay with that? So since the radius of the tower is 24 feet and the roof is covered with a 1-inch thick layer of ice, approximate how much the ice weighs. Ice weighs 60 pounds. Ice. What we're trying to do is we're trying to weigh the ice. Weigh the ice, better know how much ice is there. And the ice should be the change in volume as the tower grows from 24 feet in radius to 24 feet and 1 inch. Right? So change in volume as you go from the original tower to the tower plus 1 inch, that change should be how much ice is there. And we're going to approximate this heating. So for our particular problem, what is dV going to be? No dV for the entire volume. It's a derivative of this, which what is the derivative of this animal? This is dV, so don't forget what else we need. Not plus times dr. By the way, your units should match up. This is a good gut check. Your change in volume should be cubic feet or whatever. This is square feet, and then another foot, so that's cubic feet, so that matches up. Now, to make this work, we need numbers for R and dr to make this work. What number are we going to have for R? 24 feet. I agree. That's the way to go. How about dr? Okay, good. 1 inch, which is 1/12 of a foot. Everybody okay? So let's approximate how much ice we have here. my shell of ice is approximately, which is 2 pi times 24 squared times 112. So that's gonna be 4896. So I get about 96 pi. It's a lot of cubic feet in it, but 96 pi. So how much ice is on this thing? If ice weighs 60 pounds, cubic foot, and actual movement, then this is about about 60. So, that's like 17. Pretty good. And is it an overestimate or an underestimate? Because actually, my DV is not exactly right. The exact computation is a little bit more complicated. So this shortcut, kind of a field mapping kind of estimate. Is it an overestimate or an underestimate? Good. Pause. I don't care about the 235. And actually, I don't even care about this. This thing looks basically like a cubic like this. Right? It's basically like white. What we've done is 24 and 24 plus 1 inch, not to scale. And we're using the tangent line to approximate this. And that's a terrible thing. Notice that because of the concavity of the curve here, the tangent line, which is basically what is feeding my numerical approximation, is actually under the curve. The curve is actual. But the tangent line is under it, so it's giving me an approximation that's a little bit too small. So it's actually a little bit heavy. Okay. Any questions? Okay. Other questions? Suppose you have a differential function, you want to approximate its root r. For ease of this problem, you may assume that f of x has a. So in part A, it says if x0 is the original, is the initial approximation, explain why x1 you get Newton's method is the same result you would get from using linearization to approximate it. There's not much here. Right. So we've got a function, and it's got one root, so. And here it is. Suppose you have initial approximation, x zero. What does Newton's method do? Newton's method draws a tangent line at this point. Right? To give you this approximation. What does a linearization do? Linearization draws a tangent line. So it's going to give you the same thing. Because Newton's method in the first, after the initial approximation, the first tangent line is the same. And that's it. You're basically doing the same thing. Newton's method, you take your thing and you make the linearization at that point. That's what you're doing, because you're finding the tangent line when you find its intercept. So if you use the tangent line, find the root. If you approximate the point by the tangent line and find the root, that's the same thing Newton's method is going to find the next approximation. That's it. Nothing fancy there. And in part B, assume now that the second derivative is positive for all x. Is x1 larger or smaller than the actual root? Or is there not enough information to tell? If there is not enough information to tell, what other information would answer this question? So it says, assume the second derivative is positive. What does that mean? Second derivative is positive. So what picture should that look your head? Concave up, the function should be smiling. So it has to look like this. Very happy with it. Here's the root. Second derivative is positive. Is x1 larger than smaller than the actual root? Well, let's try a couple. Suppose x0 is here. There's x1. Smaller or larger? Say x0 is here. X1, smaller or larger? What's the answer? There's not enough. I told you. So for this function, the approximations, no matter what, the next approximation will always be larger. But I made an assumption about this function. I did draw it concave up, but what did I assume? Well, where R is at really doesn't matter in the big scheme of things. There's another assumption I made about this function when I drew it. I assumed this function is inverse. Right? What if the function is this? Notice now that I've still got all the information to follow. It's still smiling, right? The only difference is it's going down instead of looking up. What happens now? One is going to be smaller, and this is true if you come down from the other side too. Here, say x0. So there's actually, although the concave does help, but it helps me through. Other question. What's in it? Sure, do you have one in mind? Oh, here's. Um. A normal window. Right. By surmounting a rectangle with a semicircle. So I think this is called. Anyway, so the idea is you have a semicircle here, radius R, and so it's like here is H. So you've got this window that's a semicircle on top of the rectangle. Perimeter is fixed at 100 feet. Maximize. This is a problem that an architect. You've got some fixed parameter because of materials, whatever. Right? What do you want to do? You want to make this window have as big an area as possible because it lets the most sunlight get out. Right? If sunlight is a thing. So, yeah, I guess that's kind of a big one. But we'll go with it. Let's find the maximum area and how to build this. Okay, perimeter is 100 feet. What's perimeter? Okay, good. We got two lengths of edge. What's this length here? Good. You are here. So we'll see what we get here. Two R's, two H's. And then you gotta walk around this semicircle, right? Good. So that figure's gotta come to 100. Two R's, two H's, power, that's, yeah, later on, that's fixed. And what we're trying to do, we're trying to maximize area. And what is the area here? Okay, so now we got the box. Right. That's the bottom part. And then we've got the semicircle part here, which is what? Okay, we got our usual problem, too many variables. I don't know about you guys, but I'd rather solve for H, put it for H. That's easier to solve the problem. So let's try. When we press to digitate this, 2H is 100 minus 2R minus power. So minus 2 plus power. There we go. So H is equal to 50 minus 1 plus pi 2, whatever that written. So this allows new and improved A 2R this is mass. 50 minus 1 plus pi over 2 R plus 1. This is a mess. You don't have to do this, but I'm going to do it. Just to we'll probably thank ourselves later. This is 100R. This is going to be R squared 2 plus pi R squared plus 1/2 R squared 1/2 power. 2 plus pi. So area is equal to 100. Minus, that's minus pi. And I know that this is going to be max at this point. See if I know why? It's going to be max. Oh, we're fine, except for it. Yeah, I guess what, what you could do if you were like really kind of stupid about it, but you could let R be 0, right? And then basically you just got this slip, H up and H down, which is kind of stupid, but it's not going to be aired. But I don't see any limitations. How big can R be? What happens is H goes to 0. Actually, what happens, when you prove your equation, the smallest H would be a 0, if I agree with that, can't be negative. If that's 0, then R is 100 over pi plus 2. Actually, that's something that happens. And what happens when H equals 0? That's what that means. The circle gets bigger, this is smaller, and essentially what you get is a semicircle. It goes across 2R and then pi R here, and that's where the 2 plus pi is the denominator. I just take the rest. 100 minus 4 plus pi R. I'll bring that 2 down, I'm going to flush it in there. 4 plus pi. And let's set this equal to 0. I get 4 plus pi. 100. Where R 100 over 4 plus is this in my critical range? Certainly is. I mean, certainly this number is positive, right? So it's greater than zero. And the biggest it can get is about 100 divided by 5. This is 100 divided by 7, it's small, right? So what do we gotta do? Well, we just gotta back up, do it. Let's just check all the endpoints of the critical numbers. What happens at A of 0? Well, let's look at my formula here. When I get 0, I get 0. A of 100, that's 2. Or, I mean, it's just awful, isn't it? This is 100 times R, so it's going to be 10,000 5 plus 2 minus 2 plus 1/2 pi times 100 over pi plus 2 quantity squared. Precious. Both sides. Quick way. Isn't this what happened to the other endpoint? What was R? Radius was 100 over pi plus 2. This is what happened. It should be a series over there. It should be this 1/2 pi times the square. Which is what you should get from simplify. But actually, you don't need to know this number. And this is worse. Goodness, this is 100 to 100 is 10,000 over pi over 4 plus pi minus 2 plus 1/2 pi over 100 4 plus 5 squared. Which one of these is biggest? Oh, actually, this one has. There's a way that I know this. There's a couple of ways. So here's the way I can do this without really numbers. How many critical numbers do I have? Let's go one, didn't we? Only one critical number. And this function, even though we only care about it on this interval, this function is defined every day. Right? In fact, what is this function? This is parabola. And the multiplier of the square term is negative. So somehow or another, this has to look like this. Look at the second derivative function. It is minus 4 plus pi. The second derivative test says the critical number has to be a maximum. Critical number max. And so what happens is the function whatever this critical number was, 104 was fine. It increases up to here and decreases. So this is an absolute. You don't even need to have the numbers with this. This thing right here is a parabola. The multiplier of the square term is negative, so it's an upside down parabola. So the critical number has to give you an absolute max. I don't have to plug in the numbers. I just know that it's going to give me. Right, okay? If you plug in the numbers, of course, you can get it. This one's the big one. This one's medium size, and this one's here. Okay, any questions? Okay, others. Yeah. Oh, cut 4 pieces out of the box and folded it up? Yeah. Yeah, sure, sure. I'll do this generally, so suppose you have a box. Like this, oh, well, you have not a box, but rectangular piece of cardboard. The sideways from A. Square. And what you want to do is you want to cut corners, cut little square corners out of every one. All the same size. If I do this right, then I can now fold this up into a box. This. So. Maximize. Volume. Of the box. Well, if we're going to maximize volume, we need equation volume here. What is the volume? Okay, so what we need to, this, of course, the little black thing inside there's square, right? So what's this one here? A minus 2 lengths bags, get both of these, and ditto here. Great. So what's the volume of this box? Good. Because the base of that will be A minus 2x squared, right? It'll be the little black square inside there, and then you fold those flaps up, and it'll have height of X. Right? Now, maybe the trickiest part of this is the placement. How small can X be? be zero, right? I mean, there's nothing stopping you, there's nothing in the equation that's messing you up. It's a stupid attempt at making the box, because I think the start with square, it's a whole. But you can do it nonetheless. How big? Good. Because remember, you're making these cuts from both sides. The biggest you can make X is halfway across. And if you do it halfway across, you're cutting the whole box away. In fact, each one of these little corners that you take out are no longer corners. They're a quarter of the entire box. You throw everything away, and now you've got nothing. By the way, both of these silly solutions should give you zero volume. And we'll see that. So let's take the derivative of this. Derivative of X is 1 plus X times the derivative of this, which is 2. A minus 2X is 1 power negative. This should be square. X. Pull an A minus 2X out. And this leaves me with a single A minus 2X. And I guess that's minus 4X. So I get B prime A minus 2X and A minus 6X. I get two critical X equals 1/2 A and X equals 1/6 A. And both of these numbers are in my neighborhood, right? In fact, 1/2 A is at the end, so let's save you the trouble of one endpoint. And 1/6 A is in the interiors. Notice that not A, B of 0. When I plug in 0 to this, I get 0. And notice when I plug in 1/2 A to this, I get 0. And we predicted this would happen. X equals 0, that gives me 0. That's just leaving the cardboard on the table without cutting anything. And A is 1/2 X means you put everything away and you put left. So you put 0. So if this interior critical point, 1/6 A gives me something other than 0, because and it's positive, and that gives me the max. Okay, so it's 1/6 A, and this A minus 2 times this is 1/3 A squared. So that is going to be 4/9. This is 2/27. That's maximum volume, and you get it by making the cuts basically 1/6. Any questions? Okay. Others? Yes. Got until tomorrow? All right, well, go home and study, but not too much. If you need plenty of rest, and we'll see you tomorrow.